So in this section, we're going to talk about solving systems with no solution or an infinite number of solutions. So let's look at a system that would have no solution. So we're going to solve it with Gaussian elimination. So we're going to place the system into a matrix. And then we're going to go through the same steps as we did in section 2.1. So we have the 1 in the top left. That's good. So the next step is to get the zeros underneath in that same column. So we use row 1 to make that happen. So we do negative 2 times row 1. Add that to row 2. So that'll get that 0 there that we want. And then the other spots would be negative 1, 10, and 1. Row 1's not changing, so we can feel free to just copy and paste row 1. And then to get the 0 in that last spot in the first column, we can do negative 3 times row 1 and add that to row 3. So that'll get the 0 there. And then the other numbers will be negative 1, 10, and 6. Okay, so what's next? We want this to be a 1. So we can multiply row 2 by negative 1 to make that happen. Okay, and then next we want the 0 underneath that 1. So we can get that by adding row 2 to row 3. So we can do row 2 plus row 3. So we'll get 0, 0, 0, 5. And the other rows did not change. And so you'll notice that last row is interesting looking. So if we translate this last row back into equation form, this would be 0x plus 0y plus 0z equals 5, which this is a false equation because there's no way we could plug in any values for x, y, z to get 5 on the other side. So this means the system has no solution. So no solution. And we say the system is inconsistent. So that's always what a system with no solution will look like. You'll have some row where you have 0, 0, 0, and then some non-zero number on the right side. This time we're going to look at a system with an infinite number of solutions. And so we're given this system of equations, and we start by putting it into a matrix. And then, so I have all the row operations that would be necessary to get it into row echelon form. And so, you start by making that 301, and then you make the zeros underneath through row operations. Okay, and then you get that 1 in the middle to be a 1. And then after that, you get the 0 underneath right here. And so by doing all these row operations, you'll notice that this last row ends up being a row of all zeros, which implies that there's an infinite number of solutions to this system. So if we translate this last row of this matrix back into equation form, we get 0x plus 0y plus 0z equals 0. Or 0 equals 0, which is a true equation. Okay, which means this system is dependent on the top 2 rows only. Okay, so we end up dropping that last row because it's irrelevant for finding the solutions. So we just focus on the top 2 rows. So this is our new matrix. Okay, and so the new system would be x minus y minus 2z equals 2, and y minus 10z equals negative 1. Now the goal is to get x and y in terms of z. And so if we isolate y in this equation, the second equation, you would end up getting y equals 10z minus 1. Okay? And then we do some back substitution to get x. So we're going to take this expression that y equals and plug it into that y on the first equation. So we get x minus 10z minus 1 minus 2z equals 2. And we solve for x. So distribute the negative. And when you move everything to the right side, you end up getting 12z plus 1. So our solution is an ordered triple, in terms of z, would be 12z plus 1. So that's the expression of x in terms of z. And then 10z minus 1. And always z at the end. So z can be any real number we want to. So, but this is the solution we see in green. And so what we can do is, this represents the infinite number of solutions in our system, but we can plug in any value of z to represent some solution. So if we let z equal 1, for instance, one solution would be 13, 9, 1, just by plugging it in. Or if we plug in -1 for a z value, we would get -11, -11, -1, and so forth. So we could plug in 0. We could let z equal 0 to generate another solution. So that would be 1, -1, 0. So you could do this all day, just letting z equal any arbitrary number. All right, so here we have this system, and we want to solve it through Gauss-Jordan elimination. And so we start by putting the system into matrix form. And we want to get the zeros underneath that top one. So we'll do -2 times row 1 and add that to row 2. So that'll get us 0, -1, 5, -4. We're not changing row 1, so we could copy and paste that as well. And then for row 3, we just need to do negative row 1 plus row 3 to get that 0. And then the other numbers would be -1, 5, -4. All right, so you'll notice those last two rows are the same. So that should indicate that we're going to get infinite number of solutions, but we want to keep going with the process of Gauss-Jordan elimination. So we want to get that number to be a positive 1. So we multiply row 2 by -1. The next thing will be to get the 0 underneath that 1, so in column 2. And if we just add row 2 and row 3 together, we can get this to happen. So row 2 plus row 3, we'll get 0, 0, 0, 0. So this indicates there's an infinite number of solutions. So this system is dependent on these top two rows. All right, so we want to get this matrix as close to reduced row echelon form as possibly can. So what can we do? We can get this 0 here where that -2 is. So we can multiply row 2 by 2. So we can do 2 times row 2 plus row 1 to become our new row 1. So that'll get 1, 0, -11, and 13. So row 2 did not change. Okay, so we could have dropped row 3 at this point also. It's just going to say zeros. But what we'd want to get next, if we could, is we would like to get zeros in these spots. But since we know we have infinite number of solutions, there's no way we can use row 3 to help us out. So at this point, we are done. This is reduced row echelon form. And that's as far as we can get. So we stop here, and we translate these first two rows back into equation form. So we got this, and we just isolate x and y in both of them. So we get x equals 11z plus 13, and y equals 5z plus 4. So there is an infinitely many solutions, and the form of these infinitely many solutions is still an xyz. So x is 11z plus 13, y is 5z plus 14, and z. Okay, so we want to talk about non-square systems. So a non-square system is where the number of variables is different from the number of equations. So for instance, we have 2 equations and 3 variables on number 4. So when we draw the matrix, you'll see it's a little less square-like than the other matrices we've been dealing with. So we got a 2 by 4 matrix. Okay, and the goal is still the same as the previous way we have solved matrices. So we have just 2 rows, 4 columns. So we still want 1s down the diagonal and 0 underneath. And we do not care about the other spots, at least for Gaussian elimination. Okay, so we want a 1 in the top left first. So how do we get that to happen? Well, if we just switch row 1 and row 2, well, that'll make it happen. So we'll switch row 1 and row 2. All right. All right, what's the next thing to happen? We want a 0 underneath. So we want this to become a 0. So we can do this by using row 1. So we can multiply row 1 by -3 and add that to row 2 to get this to become a 0. All right. So that'll get us 1, 3, and 2. Okay, so that's convenient. So we met our goal. We have 1s down our diagonal, and we have 0s underneath. So the next thing we can do is we can write the equations for these 2 rows. So we have x minus plus 2y plus c equals 8. And we have y plus 3z equals 2. Okay, so we can isolate y in that second equation. So -3z plus 2. So that'll be part of our solution. So I'll also say anytime we have a non-square system, most of the time we're going to have an infinite number of solutions. There could be a time where we get no solution, but most of the time, infinite number of solutions is what's to be expected. All right, so next then we'll plug into the first equation. So we have x plus 2 times -3z plus 2 plus z equals 8. Okay, and then we're just going to isolate x. Okay, so if you get x by itself, you'll see equals 5z plus 4. All right, so our final solution is an ordered triple in terms of z. So x first, right? So 5z plus 4, comma, -3z plus 2 for y, and then z. Always z in the end if it's an infinite number of solutions.